Hello everybody. In this video we're going to go through questions 17 through 20 utilizing the pKa values on this table here, and then we'll go through annotating a voltaic cell. So here are some of the values that we've been looking at. Let's use them to answer the next two questions. So both of these questions ask what is favored in the acid-base reactions that are given. So remember, to answer this, we need to look at the pKa of the acid and the conjugate acid. So if we want to quickly label everything in these problems, first let's start with 17. So if we look at these, which molecule loses a proton? Which reactant loses a proton? Which one's acting as an acid? That's right, there's our acid, and meanwhile our amide anion is acting as a base. Very cool, very cool. Meanwhile, on the product side, the acid becomes the conjugate base, and the base, once it gains a proton, becomes the conjugate acid. Now remember, to predict which side is favored in equilibrium, we only need to look at the pKa's of the acid and the conjugate acid. So let's do just that. So looking at this table, we can see here is our acid, and where's our conjugate acid? Our conjugate acid is ammonia right here. So these are the two values that we'll use to answer this question. So this molecule has a pKa of 8.9, and then our conjugate acid has a pKa of 36. So it turns out this molecule is actually surprisingly acidic for a carbon-hydrogen bond that we're breaking, because the product, the conjugate base, has resonance. So actually 8.9 is pretty notable for a CH bond. Anyway, all we have to do now is compare the two values. Whichever side has the larger, the most positive value of the pKa, that's the side that's going to be favored. So in this case, we can see 36 is substantially larger than 8.9, so our equilibrium is going to lie that direction. Since the products are heavily favored here, we are going to say that the KEQ then, the product reactant ratio at equilibrium, is going to be much greater than 1. So the equilibrium is always going to lie on the side with the most positive pKa value, unless the pKa's are within 2 of each other, in which case the relative strength of the acid and conjugate acid are pretty similar. We're going to say that those have more of a true equilibrium where the KEQ is closer to 1. So now let's do question 18 the same way. So let's find the pKa values of our acid and conjugate acid. So these two molecules right here. Let's jump back to the previous slide. So here we have our acid, that is ethanol, and our conjugate acid in this problem is this molecule right here, carbonic acid. So our pKa's are 16 and 6.4. Once again, the equilibrium is going to lie on the side with the most positive pKa value. So it is going to go this direction. Since the reactants are heavily favored here, the product-reactant ratio at equilibrium is going to be much less than 1. We'd have fewer products, much more reactants, so that ratio is going to be less than 1. Okay, so for this problem, we're given this, this nice molecule here, appears to be a tripeptide of some variety, and we're asked to find the total charge at a pH of 8. So remember, there's just 2 rules that we need in order to be able to annotate this and figure it out. And those rules are, if the pH of the solution is less than the pKa, that means we're looking at a solution that is acidic enough to ensure that our functional group is protonated. So if the pH is less than the pKa, our functional group is going to exist in its protonated form. And remember, the 2 functional groups that we're focused on are carboxylic acids and amines. Now, on the other hand, if the pH of the environment is greater than the pKa of the functional group in question, then the environment is basic enough to rip off the proton, and our functional group will exist in its deprotonated form. So using this and considering our functional groups of carboxylic acids and amines, we can go through and we can annotate this molecule that we have. So we're going to go one functional group at a time. Just to add to this though, let's remember what it looks like if we have a carboxylic acid that's protonated versus deprotonated. So here we have a generic carboxylic acid. It's got its proton right here, so this is the protonated form. Oh. If the pH is greater than the pKa of a carboxylic acid, the environment will be able to rip off that proton and we'll end up with a carboxylate, which looks like this. So this is the deprotonated version. And this is significant because we can see here that once we take off the H+, that oxygen ends up having a negative formal charge. So this is going to contribute to the charge on a molecule. So now let's consider how amines are different from this. So if an amine is deprotonated, if it exists in its neutral form, it looks like this. Okay? And if that gets protonated, so if the pH of the environment is greater than the pKa of this particular chemical species conjugate acid, then we end up with the protonated version, which notice now that once that nitrogen gains a proton, now we have a positive formal charge. That's also going to contribute to the overall charge on a molecule. So notice the distinction between carboxylic acids and amines. Carboxylic acids, when they're protonated, are neutral, and if we take off that H+, we end up with a negative formal charge. Whereas, in terms of bearing a charge, it's the opposite for amines. Amines, when they are protonated, have a positive formal charge, and if we pull that proton away, then we end up with a neutral charge. Now, with that in mind, let's go through and annotate this molecule. And let's start with this carboxylic acid over here on the left. So let's start with this proton. So notice that for this first one, so we're doing this at a pH equal to 8. So how does the pH compare to our pKa? So the pH compared to the pKa here is greater than, which means this carboxylic acid is going to be deprotonated. We're not going to have a proton on here, so it will have a negative formal charge. And this is what we're going to do with all of these various functional groups. Next, let's move up to, let's do this amine up next. So let's do this particular nitrogen here. So notice the pKa of the conjugate acid is 6.3. So if the pKa of the conjugate acid is 6.3, how does it compare to the pH? Well, once again, the pH of the solution is greater than the pKa, which means that this nitrogen here is going to be deprotonated. So I'm just going to put a lone pair on there just to signify that that hydrogen is not, in fact, there. I didn't draw the lone pairs in on the oxygen, but it would have 3 lone pairs, the one that we looked at before. Okay, so now we've got 2 down, we've got 2 to go. Let's do it. Next, let's do this amine right here. So, for this amine, it's got a pretty notable pKa, or a pretty high pKa, I should say, not really notable. I guess all pKas can be considered notable. But the pKa of the conjugate acid is 9.4. So if the pH is 8, well, now we're looking at a situation where the pH is less than the pKa. So that means that this is going to actually be in its protonated form. And if it's protonated, it's going to have a positive formal charge on it. Which leaves us with this nitrogen here. We can check, we can see that the pKa on this nitrogen is 9, which means that once again, just like the last one, in this situation the pH is less than the pKa, which means this environment is acidic enough to protonate this. It's going to have a positive formal charge, and we are done. Okay. So now let's tally up our various charges. So for the carboxylic acids deprotonated, this is contributing a total charge of -1. The amine adjacent, that's going to be 0. And then the other 2 amines are both contributing a +1 and a +1. So -1 plus 0 plus 1 plus 1, we get an overall charge on this molecule of -1. This next question says, what is the oxidation state of hydrogen and hydrogen peroxide? So remember, in any compound where you have a group 1 atom, always assign oxidation numbers to the group 1 atom first. Each hydrogen is in its +1 oxidation state, as group 1 elements will always, at least for our purposes, take on whenever they're in a compound. But there's 2 of them, so I like to put the total oxidation states contributed from all the atoms below. So 2 hydrogens, each with +1, so a total of +2, which means that our oxygens must be a total of -2. Since there are 2 of them, that means that each oxygen is carrying a -1 formal charge. So our answer is going to be -1, and that's always going to be the case for oxygen for a peroxide. Okay, now for main event, we're going to diagram a voltaic cell. So the first thing that we're always going to do when diagramming a voltaic cell is draw two compartments, and they don't have to look great. So I'm just going to draw some beakers. You can be creative with your glassware, I suppose. There's beaker number 1. It's fine. And then beaker number 2. Draw it in. Make it a little 3D. Neat. And now let's add in some water. Splash. Splash. And some electrodes. So we need some electrodes here. So I'm just going to draw a wire that connects the two compartments. And then I'm going to draw in, there we have electrode 1, and here we have electrode 2. Okay, we have our basic setup, and I'm just going to touch this up a little bit. First, let's make this a little bit bigger so it's easier to see. I'm going to leave some room on the side to analyze the half reactions. Okay, and now let's just make it a little bit less wobbly. Wobble with me, yeah, yeah. And just to enhance our 3D effect here, I'm just going to erase that, make it in between the two, and erase that. But, you know, you're not going to be graded on the art here. It's more important to know the art of the voltaic cell. What's going on here? So now let's create our solutions. It doesn't matter which side we make which. I'm just going to adhere to the order in the problem. I'm going to make the left side lead and the right side copper. So let's do that. So there we have our lead. Over here I'm going to make this copper. All right, and then we can see here the concentrations of the solutions. We've got 2 molar lead nitrate. And remember, the nitrate is just there to help counterbalance the charges. It's just there to make sure that we have an electrically neutral solution. So in here we have our 2 molar lead nitrate. Cool. And on the other side we have copper nitrate. Again, the nitrate is just there to counterbalance the charges. So it's 3 times 10 to negative 4th molar Cu2+. Okay, so there we have our solutions. And, well, as this is written, this has a fundamental problem. And what would that problem be? Well, first, before we discuss what that problem is, let's figure out which way the electrons are going to flow. So let's compare the respective reduction half reactions of both of these. So what I recommend doing is writing out the 2 possible reduction reactions, one for each compartment. So we'll write out our respective half reaction and the corresponding potential. All right, so first let's look at lead's reduction potential. The reduction for lead, 2+, to be reduced to lead solid is Pb2+, aqueous, plus 2 electrons yields lead solid. Okay, cool. And what is the standard half reaction, the standard potential that goes with that? Well, it is negative 0.126 volts. Okay. Can we do better? Let's find out. Let's look at copper's reduction. So we have copper 2+ plus 2 electrons yields Cu solid. And this has a fairly favorable reduction potential of 0.337 volts. Okay, cool. So now we just have to compare and see which one is more favorable. That's the one that's going to be preferentially reduced. So whichever one's most positive is going to get the nod, which is going to be the copper 2+ reaction. So I'm just going to write red next to it for reduced, and then we're going to take the other reaction, we're going to flip it around. So there's the oxidation of solid lead. And remember, whenever we flip the reaction, we flip the sign. So this becomes positive 0.126 volts. Great. Now I'm just going to cross out this here because this actually isn't going to happen. We're not going to be reducing lead in this particular reaction. So there we have our half reactions. We've actually already answered the next question as well, which is cool. So now I'm going to draw in which way the electrons are flowing. So they're flowing toward the copper. The copper is what's getting reduced. There's an electron, just showing that it's going this way. Our electrons are heading that direction. Now, as this is written, this would have a fundamental problem. And what is that fundamental problem? Well, if electron density is building up on this side, it would be building a negative charge. And it would be building a negative charge very fast. Would electrons inherently be attracted to a negatively charged container? The answer is no. So we need to do something to complete the circuit to make sure it remains electrically neutral so the electrons can keep getting drawn across over to that side. Which is why we have to add a salt bridge. A salt bridge, yes indeed. And the salt bridge is just going to give us a source of an electrolyte solution to help make sure that we complete the circuit and keeps both sides electrically neutral. So this would have, most frequently, we have salt bridges that consist of sodium, because it always forms completely soluble salts and won't cake out, and nitrate for the same reason. So the way that the salt bridge functions is that as the electrons flow into this compartment here, it would get more negative if not for the cations that can flow into this side. There's a semi-permeable membrane down here that it'll use to leak out into the solution. On the other hand, and on the other side, over at the anode, the anions, since electrons are leaving this compartment, the NO3- will replace the negative charges that are lost. And why is that significant? Well, electrons are going to be attracted. If the one side's losing electrons, it's going to become more positive. And electrons aren't going to be able to leave. They're not going to be inherently able to move away from a positive charge because negative charges are attracted to positive charges. So, by replenishing the negative charge here, it makes sure that the electrons are not too attracted to that container to leave in the first place. Finally, we have to label the anode and the cathode. I always like to just think about it as, remember, electrons always travel from A to C. They always travel in alphabetical order. So electrons will always travel from the anode to the cathode. As long as you remember that, you are going to be good to go. So labeling these, which side is the anode? The side that's losing electrons where oxidation is taking place. Over here is our anode, which makes the side where our electrons are going the cathode. Cool. Okay. And there we have our diagram with our salt bridge, with the electron movement on there. We have the anode and the cathode labeled. We are good to go. Now let's answer these other questions. So this question says, what are the half reactions and corresponding E standard 1/2 at the anode and cathode? What is the overall reaction and the E standard? Well, we already have the half reactions and the half potentials. Let's plug those in. At the anode where oxidation takes place, there's our oxidation half reaction. Now for our reduction. Okay, there we have our reduction half reaction with a positive 0.337 volt. And then when we make our overall reaction, just remember we need to make sure that the electrons cancel out. And indeed, in this case, so 2 electrons here, 2 electrons here, these will work as is, but always make sure that the electrons are balanced. So we can combine these together and get our overall reaction of solid lead plus copper 2+ yields lead 2+ and copper solid. And then, just remember to get the overall E cell, all we have to do is add together these two potentials. They're both positive. And we will end up getting that the overall E cell is equal to 0.463 volts. Okay, so now we're good with this part. Now let's go answer the other questions. So part C says, under these conditions, now it's bolded, italicized, and underlined. This probably means it's worth noting. What is the E cell? Well, are we under standard concentrations here? No. The concentrations are most assuredly not 1 molar of everything. So, whenever we have non-standard concentrations for an electrochemical cell, we need to use which is E cell is equal to the standard potential, which we've already saw for, minus 0.0592 divided by n, the number of electrons transferred in the balanced reaction, times the log of Q. Now, before plugging in anything into this reaction, I recommend writing out the expression for Q and solving for it. So let's do just that. Well, there's our reaction. So that means Q is going to be our products over our reactants. So our expression for Q is going to be the lead 2+ concentration over the copper reactant concentration. Remember, we don't include solids in this expression. So plugging in the values that were given from the question stem, it's 2 molar for the lead and 3 times 10 to the negative 4th molar for the copper 2+. And this ends up equaling 6.7 times 10 to the 3rd. Okay, now let's plug this into our Nernst equation. E cell is equal to our standard potential. We solved for that before, that's 0.463 volts. Minus 0.592. Oops, something happened to my 592 up there. I'm just going to fix that 2 up. Also, sorry. Whoa, hold the phone. I didn't write in a 0 there. I'm missing a 0. So, let me fix that up. Sorry about that. It should be 0.0592, not 0.592. So, please make sure that you have that extra 0 in there when doing the calculation. Okay, so now let's get to calculating this. So, 0.0592 divided by n, the number of electrons transferred, which were 2 electrons. Remember, we can get that from looking at our half reactions, times the log of Q, which is 6.7 times 10 to the 3rd. So multiplying this all together, we get 0.463 volts minus 0.113 volts, which ends up equaling 0.350 volts. Cool. The next question says, into which compartment would the cations flow? Well, cations always flow into the cathode from the salt bridge. The anions always flow into the anode from the salt bridge. Next question says, what is the KEQ of this cell? So to relate potential and equilibrium constant, we need to use a modified version of the Nernst equation. Its E standard of the cell is equal to 0.0592 divided by N times the log of KEQ. This is what we can use to relate potential, voltage, and our equilibrium constant. So let's plug in our values. For this equation, we always plug in E standard. So we're going to use our standard value, which we calculated was 0.463 volts. Set that equal to 0.0592 divided by N, which is 2 moles of electrons transferred, times the log of KEQ. And now we're going to multiply the 2 through and divide both sides by 0.0592. So we get 15.36 once we algebra that out. Now to get rid of that log, we need to do 10 to both powers, and that will effectively cancel out our log. And we'll end up getting our KEQ, which is an impressive 4.38 times 10 to the 15th. Cool. So then the final question says, how much work can this voltaic cell do under these conditions? Again, under these conditions means we need to consider the actual E cell. We need to consider the concentrations that were given. So we're not going to use E standard for this. We're going to just use regular old E cell. And to relate work and electricity, what we're going to use is delta G, the free energy change, equals negative N, the moles of electrons transferred. F, Faraday's constant, and E cell, the potential. So now let's plug in our values and solve for delta G. Our N is 2 moles of electrons. Faraday's constant is 96,485 coulombs per mole of electrons. And our E cell under these conditions is 0.350 volts. So now moles of electrons are going to cancel out. So let's just, and our units will end up being in coulomb volts, so what we'll end up getting is a delta G equals negative 6.76 times 10 to the negative 4th, or sorry, times 10 to the 4th, 10 to the 4th coulomb volts. And again, a coulomb volt, we can actually, it's just a fancy way of saying joules. And then we can convert this, we can divide by 1,000, and we'll end up getting the delta G equals negative 67.6 kilojoules. So that means that this could do 67.6 kilojoules worth of work. A positive E cell will always be a negative delta G. It can always do work. It's always spontaneous, etc., etc., etc. And there we have it. Thank you for your time, and dominate that exam.